Thanks a lot, Nikolaus. And we are coming to the next contribution on climate change effects on nuclear power plants. And the speaker is Professor Helga Kromp-Kolb. She is a meteorologist and climate scientist. Until her retirement, she headed the Institute of Meteorology and Climatology and the Center for Global Change and Sustainability at the University of Natural Resources and Life Sciences, Boku, Vienna. In recent years, she co-founded the Alliance of Sustainable Universities in Austria and the Climate Change Center Austria. So we are very keen to hear her expertise. Please, Helga.
Thank you very much for the introduction and for the invitation. I want to focus on one of those things that have changed since nuclear power plants were licensed, and that is climate, and what effect climate change has on nuclear power plants. I'll try to set the stage a bit by talking about climate change and how this change can affect nuclear power plants, and then I will go into coastal sites and the sea level rise problem, extreme events, and then sum the whole thing up. Climate has changed, everybody meanwhile knows, and the temperature, for instance, has risen by about 1.2 degrees on the global more outages due to lack of cooling water. These are issues that are relevant to operators and to the potential of production of nuclear energy, but it is not the topic that concerns us here. What concerns us here is the matter of risk, of what it means for power plants if their life is prolonged. And that is essentially two groups of topics. One is the coastal sites that are endangered through sea level rise. And the other is that there's more and more frequent, more intense extreme weather conditions. And these affect the safety of nuclear power plants. And that is the focus of today. Now, looking at climate change, looking here at temperature development, since about 1880, we can see temperature increase, and especially since about the 1970s, we have this continuous increase, and we have now reached a temperature increase of about 1.2 degrees above pre-industrial levels. Now that is a global average, and you can see from the large variability in those black dots along the blue line that there's a high variability from year to year. So there's not the average temperature increase, but every year can look different, and for individual years, temperature increase can be much larger than you would expect from the global average. And this is, of course, also true for individual sites. The global average is strongly influenced by the slow increase in temperature of the oceans. Land-based sites experience a much faster temperature increase. Austria, for instance, experiences about double the temperature increase from the global average. And if you look at northern countries, then it will be even larger. Now, nuclear power plants have been built in all sorts of climates, and they can be built to fit all sorts of climates. The problem is, however, that we're not talking about building a new plant in a new climate. We're talking about extending the lifetime of a plant that was built to a different climate. And this is what the problem really is. So if we look at this from a point of view, what does it mean in terms of nuclear power plants? You can see the small insert here, the number of power plants built in which decade, and you can see most of the nuclear power plants now in operation were built in the 1980s. So something happened, but
I don't know what is happening.
I don't either. I can try to share my screen again.
It works.
Yeah?
Yeah.
Okay, I hope everyone can see me. So, what? Mm-hmm. Can you see my screen?
Yes.
Okay. So what you can see in the small insert is that the number of nuclear power plants that were newly built in the 1980s is largest of all the decades, and comparing the temperature now to the temperature at that time, we have a temperature increase of about 0.7 degrees. So since their licensing, temperature on global average has changed by about 0.7 degrees. Now, if we look into lifetime extension and look at what does that mean for the end of the lifetime then, and of course that depends how long lifetime is extended, and we heard Mr. Yatsko telling us that this can be a continuous process. But if we just look at periods like 2040 or 2060, that would be the first 20-year period and the next 20-year period, then we can see that we can expect temperature increases between 0.9 to 1 degree Celsius or even 2.5 degrees Celsius if we look at business as usual scenarios. If we stay within the Paris limits of the Paris Agreement, then we are somewhere between 0.9 and 1.4. But as I said, that is a global average, and the experiences at local sites can be quite different. And also, extreme temperatures increase faster than mean temperatures, and you can see this here. On the global level, you have this dotted line in brown. That would be the global increase, and as compared to that, the maximum temperature in the temperate regions, U.S., Mediterranean, Brazil, for instance, have about a 1 to 1.5 degree warming. So that means the maximum temperatures increase by 50% more than the average temperatures. And if you go to the Arctic, you even find a factor of 3. So these global averages are not good enough to really give information about what the nuclear power plants at specific sites will meet. What temperature increase certainly means is an increase in sea level. On the one hand, because of the warming of the sea and the expansion of the water. On the other hand, because of melting ice from land-borne glaciers. And what you can see here is the expectations as they are, the scenarios as they are described within the IPCC reports for 2 degree warming, blue, and for a business as usual situation in red. The problem with sea level rise is that we don't really, science does not fully understand yet the process of melting glaciers. So if you look at the models, you get the results shown in the graph below. If you extrapolate data of melting Greenland ice sheets, as was done by Hansen and co-authors in 2016, then you find much, much larger sea level rises. That could be as much as 1.4 meters by 2060. If you subtract the 20 centimeters that had already occurred at the time of licensing in the 1980s or so, that means we still have a possible sea level rise of 1.2 meters by 2060. That is really considerable, and the power plants, those located on the shores, were not built to address this kind of sea level rise. It is not just a matter of protecting the site with some walls or some dams. It is also a question of discharge of water, discharge of wastewater from the plant, cooling water from the plant, and that can be a problem with sea level rises of this size. And as in temperature, also sea level rise is not uniform throughout the world. You can see here for the ocean areas, the land areas represent temperatures, but the ocean areas represent sea level rise. And you can see that there's a variety of about more than 1 meter of sea level rise between different parts of the world. So these average figures, again, do not really give all the information that you would need for adjusting your plant at a coastal site. Going towards the extreme events. Sorry, Wolfgang, you were not muted.
Sorry.
Looking at a list of possible extreme events that could influence the safety of nuclear power plants, categorized according to national phenomena hazards on the left column, in the middle man-made hazards, and on the right-hand side deliberate acts. If you look at the two left-hand columns, all the hazards that are colored in red are influenced by climate change. So that is about 80% of the natural phenomena hazards, and about 30% of the man-made hazards can be influenced in a detrimental way by climate change. So it's not really just looking at what does temperature change mean. It really means at looking a whole set of changes that are a consequence of climate change. Now, you can look at this also in a geographical manner. You can look at, for instance, heat waves, droughts, and extreme temperatures, which regions in the world that have nuclear power plants are subject to which of these hazards. And the red squares are a strongly growing trend, and the yellow ones are an average trend. And what you can see is that, for instance, the west coast of the United States or Southern Europe or the Near East would be really strongly affected, or regions with high trends in these heat extremes and drought extremes, whereas other areas, like, for instance, the east coast of the United States or Central and Northern Europe or Asia, a bit less affected by these developments. Looking at threats of flooding, we can differentiate between flooding, fluvial flooding and coastal flooding. The coastal parts are squares and the fluvial ones are circles. And you can see again that not every site has the same kind of, is affected in the same way. What this map, of course, cannot tell you is what the licensing procedure, what kind of leeway, what kind of margin was applied. So even though the trend may be small, the plant can be strongly affected if the margin at the time of licensing was already small. Why would we expect more fluvial flooding? Well, mainly because a warmer atmosphere can contain more water vapor, and therefore more rain can fall in heavy rain events, and this can lead to flooding, especially since a lot of the landscape is now no longer available as a sponge, but has been built over, and the water flows into the rivers faster. There's many other external hazards that you can also look at geographically, but essentially it is a question of the individual power plants looking at the hazards, how these hazards changed for their specific site. We're talking about snowfall, we're talking about gusty winds, about sandstorms, about freezing rain, about lightning strokes, forest fires, hailstorms, and so on. cooling water in and outlets can also, for instance, be blocked by blizzards or icing, but they can also be blocked by animals or plants that have enlarged their habitat due to warming of the surrounding water. And you must also consider that hazards may affect infrastructures in the surroundings. It is not just the power plant itself. There can be cascading effects that amplify small causes. So a small forest fire can develop into a larger fire, blocking the access to the nuclear power plant, for instance, or other cascading effects. And what we already noticed, there's an increasing hazard, an increasing danger of disturbances in the electrical grid. And these could be enhanced still by sudden shutdowns due to some external event. And that could destabilize the grid and cause large-scale blackouts, which of course have dramatic consequences for nuclear power plants, as some of the stress tests showed. The possibility to keep up cooling when there's a large-scale blackout is only limited. So to sum up, climate has changed significantly since the licensing of most of the nuclear power plants that are now in operation. The global averages that are generally talked about and discussed in the public underestimate the local changes. And the effects can also have a non-linear development. They can have exponential development. And there's a certain amount of uncertainty in these evaluations of what effects climate change will have, for instance, in terms of sea level rise. Therefore, it is necessary to reassess and upgrade nuclear power plants if their lifetime is extended. And the longer lifetime is extended, the more upgrades will be necessary. And the more difficult it will probably be to achieve these upgrades because the conditions change so much more. And this should be a continuous process because climate sciences are also continuously learning, continuously understanding new changes, new threats. And this should be part of a continuous monitoring to assess climate change in the specific location where the nuclear power plant is sited. Judging from what we have heard this morning and from the results of our studies, there's very little attention given to this problem, and I think it deserves a lot more attention. Thank you for your attention.